Question. You have a classification dataset containing 1,000 features and 1 million observations. Given your computational and memory limitations, how would you approach dimensionality reduction to ensure efficient model training? Handling a high-dimensional dataset with limited computational resources requires a strategic, multi-step approach. Here's how I would tackle this scenario methodically and effectively. 1. Resource optimization. Initially, I would ensure that all unnecessary applications and processes on the machine are terminated. Closing down other programs, especially memory-intensive ones, such as browsers or background processes, ensures that maximum resources are dedicated to processing the dataset efficiently. 2. Data sampling. Given the size of the data, 1 million rows, it's practical to initially perform random sampling to create a manageable yet representative subset. For instance, we could use a sample of approximately 20 to 30%, 200,000 to 300,000 rows. This smaller subset would allow preliminary analyses and dimensionality reduction techniques to be applied effectively. 3. Correlation analysis for feature reduction. I would segregate numerical and categorical variables and perform correlation analysis separately. For numerical variables, I would apply Pearson correlation, setting a threshold typically around 0.75 or 0.80, beyond which highly correlated variables would be reviewed and potentially eliminated to reduce redundancy. For categorical variables, a chi-square test would be suitable to identify correlations and prune redundant features. 4. Principal component analysis, PCA, is a powerful technique that systematically reduces dimensionality by identifying key features, principal components, that retain most of the dataset's variance. By selecting principal components that cumulatively explain a substantial percentage of variance, often around 95%, we significantly reduce the data's complexity and dimensionality. For instance, if the first 50 principal components explain over 95% of the variance, the dataset dimensionality can effectively reduce from 1,000 columns to just 50, greatly enhancing computational efficiency. 5. Online learning and incremental algorithms. If sampling isn't fully feasible or desirable, I would consider online learning algorithms, such as VowWow, which processes data incrementally without requiring the entire dataset to fit into memory at once. Such algorithms update the model iteratively, processing data in batches, thereby significantly reducing memory usage. 6. Stochastic gradient descent, or SGD. Additionally, leveraging a model trained via SGD can be beneficial due to its memory-efficient nature. Unlike batch gradient descent, SGD updates the model incrementally, iteratively improving the model without loading the entire dataset into memory simultaneously. 7. Domain knowledge application. Integrating business domain knowledge is invaluable. Leveraging insights and expert understanding, I would identify and retain features that are theoretically and practically significant, potentially discarding others less likely to influence the classification outcomes meaningfully. By combining these strategies, resource optimization, strategic sampling, correlation analysis, PCA, employing incremental algorithms, and applying domain expertise, I would systematically reduce dimensionality and computational demands, ensuring the developed model remains robust, interpretable, and computationally efficient.